Hi, I'm Fernando Pereira from UFMG, and today I shall introduce you to a few loop optimizations that we can apply on natural loops that are based on the notion of invariant code inside loops. The first optimization is to hoist invariant code outside loops. Invariant code is code that never changes. It always yields the same value. So if we have an expression like t equals a plus b, when is it invariant? Would you like to think about it? In other words, when t equals a plus b always produces the same value in variable t. This expression is invariant if either the operands are constant or defined outside the loop, or the operands are loop invariant themselves. So, I'm sure you can use this definition to come up with equations to find loop-invariant computations. I will leave that as an exercise. The optimization that moves invariant code outside loops is called code hoisting. But we must be careful because code hoisting is not always safe. For instance, consider this figure. Is it safe to perform the hoisting that we're showing here? Would you like to think about it? Well, here the computation is perfectly safe. And after we hoist the code up, that code elimination will remove the first assignment to t, which becomes dead. Now consider this case. Is it safe to hoist t equals a plus b outside the loop? Pay attention on how t is used. Well, in this case, code hoisting is unsafe. It's actually illegal because it can change the semantics of the program. If the loop does not execute, then we should assign t equals 0 to x at label L2. But the hoisting is changing that. See the program on the right, how it behaves. And in this case, is hoisting safe or unsafe? Or, in other words, do these two programs have the same semantics? Think about it. This hoisting is also unsafe because it's changing the value of t at the store instruction. See, t can be 0 inside the loop, and if we hoist t equals a plus b outside the loop, then we might assign 0 to m of I instead of a plus b. So that's unsafe. And here goes a last challenge. Is hoisting safe or unsafe in this case? Check if these two programs have the same semantics. Try to think about it. This optimization is also unsafe because it's changing the definition that reaches the store in m of j. In principle, we could assign 0 to m of j here, but the hoisting can change that. So when is it safe to hoist invariant code outside a natural loop? Here we have three conditions that show when that's safe. For the sake of time, I will not show examples that justify all of them, but you can stop the video and draw some loops to see that they must hold to do safe code hoisting. Actually, it would be possible to make them tighter. It would be possible to make them to catch more situations, these conditions. But this would be subject to another class. Let's, for now, just move on. Another important loop optimization is loop inversion. We had talked about it when we saw partial redundancy elimination. Loop inversion basically consists in replacing a while loop with a do-while loop, surrounded by a conditional block. The main benefit of it is to create a region where we can safely move invariant code. Thus, loop inversion enables condition 3 that we had seen in the previous slide. Look at it. The third condition that's enabled by loop inversion. And with loop inversion, we close this topic on code hoisting. Next class, we shall focus on the induction variables that control the number of iterations of loops, and we design optimizations that work onto those variables.